right, here we go, limits. We've got the limit as x approaches infinity for 9 over 6x minus 4. So I'm going to think about this critically before I attack it. I don't have a variable on the top, so if I plug in x equals infinity, the top is still going to be 9. But if I plug in 6 times, let me just put a thought bubble right here. You know, you don't have to do thought bubble, but I like thought bubble. 6 times infinity minus 4 on the bottom, and then there's a 9 on the top. Well, the 9 stays on the top. 6 times infinity, and again, I put an evil laugh. Just, you know, an evil laugh just helps you learn this a little bit better. 6 times infinity is infinity. And then infinity minus 4, think about it. Infinity minus 4. The number that keeps on growing to the maximum number, minus 4, it doesn't stand a chance. So this is 9 over infinity. Okay, so in other words, I don't have to do L'Hopital's rule. So if I plug this in, I get 9 over infinity. Well, even though it's not, it doesn't say 1 over infinity, think about this. 9 over 10, 9 over 100, 9 over 1,000, 9 over 1,000,000. It's getting closer and closer and closer to 0. So as x gets closer and closer to infinity, 9 over 6x minus 4 makes the denominator explode to infinity. 9 over infinity is so insignificant. It will never reach 0, but it's so close to 0, it's practically 0. Okay? So now let's take a look at the bottom where I take the same numbers. Let's say 9 over 6x minus 4, but this time x goes to negative infinity. So let's try negative 10, negative 100, negative 1,000,000, and so on and so forth. If I plug in thought bubble, 6 times negative infinity minus 4. 6 times negative infinity, you don't stand a chance. That is 9 over negative infinity. So the lowest number humanly possible, minus 4 is already the lowest number humanly possible. Let's just say it's 9 over negative infinity. So this is all my thought bubble work. And 9 over negative infinity. So even though there's a negative in there, just think about it. If I have 9 over negative 10, okay, it's a small negative number. If I have 9 over negative 100, still a small negative number, but even smaller than negative 9 over 10. 9 over negative 1,000, very, very small negative number. 9 over negative 1,000,000, very, very small. But either way, it's so close to 0, it's practically 0. And because 0 is neither positive nor negative, that means that it's going to flatline still at the neutral element. Okay? Now we're in business. Okay. All right. So I've got thought bubble work over here. 9 times infinity over 6 times infinity minus 4. Okay. All right, so 9 times infinity, let's just get that out of the way. 9 times infinity is infinity. 6 times infinity minus 4 is, well, let's just call it what it is, infinity minus 4, or infinity. So I've got infinity over, oh, let me make that a little bit clearer. There we go. Infinity over infinity. That's super confusing. That's an indeterminate form. So the idea is, think about the numerator and the denominator having a race. So in problems 1 and 2, the denominator is clearly going to beat the numerator. And over here, same thing, the denominator is going to clearly beat the numerator. But in this problem, we have no idea which is going to win the race, so to speak. The race to get to x equals infinity, which y value is going to be higher or lower or whatever. We don't know who's going to win the race. So this is what's called an indeterminate form. Luckily, you've got two techniques. You can either factor the top and bottom. Since the degree of here is 1 and the degree of here is 1, you can multiply the top and bottom by 1 over x. Personally, I'm a big fan of you-know-who. I like L'Hopital. So the limit as x approaches infinity, let's take the derivative of the top. What's the derivative of 9x with respect to x? 9. What's the derivative of 6x with respect to x? 6. What's the derivative of negative 4 with respect to x? 0. So this would be 9 over 6 plus 0 or 9 over 6 minus 0. It doesn't matter. It's still 9 over 6. But then, so now that we've got it as 9 over 6, can I reduce this fraction? Yeah. I can divide the top and bottom by 3. 9 divided by 3 is 3. 6 divided by 3 is 2. Therefore, the limit as x approaches infinity for 9x over 6x minus 4 is going to be 3 over 2, or y approaching positive 1.5. And if you don't believe me, you can check with the graph itself on Desmos. Let me pull this up really quick. So if I've got y equals 9x over 6x minus 4, not z. Come on, delete button. So we already know that 9x over 6x minus 4. We want it to go to infinity. So let me go back to the home button. There we go. So why don't I just zoom out and just follow this red graph. Look at that. Notice that 3 over 2 is 1.5. It's never ever going to reach 1.5, but it's not growing. It's not exactly decaying. The curve is mostly flat, getting flat. Yeah, that's relevant to today's culture. Flattening the curve. But yeah, I just go to x equals 400. It's still going to be 1.5-ish. And yeah, that's the main idea, is what happens as x goes to infinity, who's going to win the race. In this case, it flattens out at y equals 1.5. Okay? So then, turn the page. Let's say I've got this. The limit as x approaches infinity for 8x squared plus 3x minus 12. Well, 8 over infinity squared plus 3 infinity minus 12 over 6 infinity squared minus 11 infinity plus 14. Okay. I'm going to tell you straight up, the leading coefficient and the degree of the polynomial matter. So the highest degree on the numerator is x squared, degree 2. And the highest degree on the bottom, x squared, is degree 2. So who's going to win the battle between 8 infinity squared and 6 infinity squared? That's infinity over infinity, which I don't like. So what can I do to calm my nerves? My good buddy, L'Hopital, for the limit as x approaches infinity. So I'm going to take the derivative of the top and the derivative of the bottom. So if I take the derivative of the top, 8x squared, the derivative is 16x. The derivative of 3x is positive 3. And the derivative of negative 12 is 0. Let's take the derivative of the bottom, 12x. And the derivative of negative 11x is negative 11. Now, once again, I get my thought bubble, 16 times infinity plus 3 over 12 times infinity minus 11. Cut the nonsense. 16 times infinity plus 3, that's infinity. 12 times infinity minus 11, that's still infinity. What does L'Hopital rule say? L'Hopital says, if it's still an indeterminate form, do it again. L'Hopital. So I still got the limit as x approaches infinity, but now I'm going to differentiate the top and the bottom again. 16x, the derivative of that is 16. Plus 3, the derivative of plus 3 is 0. 12x, the derivative of 12x is 12. The derivative of negative 11 is 0. So do I have infinity over infinity? No. So now I'm going to see what happens if I have 16 over 12. I'm going to reduce this fraction. I can divide the top and bottom by 2. I can divide the top and bottom by 4. And looks like nothing bigger than that. So divide the top and bottom by 4. So what this means is 16 divided by 4 is 4. 12 divided by 4 is 3. So as x gets closer and closer to infinity, the curve starts to flatten out at y equals 1.33333333 repeating. So basically, you notice that 8/6 can be reduced to 4/3. So really, I could have just done this the entire time. But be careful in the next two problems. So let's say I just increase the degree on the top by 1. So let's just say I care about, let's just say I plug in x equals infinity on the top and the bottom. Well, if I plug in x equals infinity, I get 8 infinity cubed, and I don't really care. And 6 over infinity squared, and I don't really care. So the idea is, I just realized this is, it just dawned on me, this is kind of like sports. LeBron James and the other guys versus Stephen Curry and the other guys. or you know what I mean, in the 80s. Magic Johnson and everybody else versus Larry Bird and everybody else. No. But no, it's literally the leading coefficient. It's the leading degree and everybody else. Notice that we can use our common sense. That infinity cubed over infinity squared, even though they're both going to be infinity, the numerator is going to be bigger than the denominator in the long run. So I'm going to play your game. I don't like this, so it's an indeterminate form. So who's going to help me out for indeterminate forms? My good buddy, L'Hopital, my best friend in the whole wide world. My friends are historical mathematicians. Anyway. So let's take the derivative of the top and bottom. The derivative of the top is going to be 8x cubed. That's going to be 24x squared plus derivative of positive 3x is positive 3. And the derivative of negative 12 is, you're gone, 0. Let's take the derivative of the bottom now. 6x squared, that's going to be 12x. The derivative of negative 11x, that's going to be negative 11. And the derivative of 14 is, you're gone. You're a constant. Now, hey, infinity over infinity still yet again. My good buddy L'Hopital will bail me out yet again. The limit as x approaches infinity for the derivative of the top is going to be 48x. And the derivative of positive 3 is, you're done. And now 12x, the derivative of that is 12. The derivative of negative 11 is 0. So in the end, I get 48x over 12. What happens if I plug in x equals infinity? Well, I can plug in infinity on the top, and since the bottom will always be 12, it's no contest. It's no 48 times infinity divided by 12, that's infinity over 12, or infinity. So as x gets closer and closer to infinity, the numerator wins that race. So huge infinity over not so huge infinity. What a weird concept, I know. The numerator wins, so it gets closer and closer to y equals infinity. Okay, and let's go to number 6. Okay. This will be the last problem of the day, and then I'll give you guys the tips. So I just kept the same numbers, but I made the degree of the top 2 and the degree of the bottom 5. And you know what? Let's see what happens. So you get the idea. I care about these two. I care about the star players of the numerator and the denominator. The leading degree, the leading coefficient. So 8x squared over 6x to the 5th, or I'm going to plug in x equals infinity. No contest. The denominator is going to win this race. But let's show the work. So we can agree that if we apply direct substitution, it's going to be 8 infinity squared over 6 infinity to the 5th power. My good buddy, L'Hopital, tells me that the limit as x approaches infinity has the derivative of the top over the derivative of the bottom. 8x squared, the derivative of that is 16x. The derivative of positive 3x is positive 3. And the derivative of negative 12 is, you're gone. You're toast. The derivative of 6x to the fifth, that would be 30x to the fourth. The derivative of negative 11x, that's negative 11. And the derivative of positive 14 is your toast. So that it is what it is. Let's pretend we plug in x equals infinity. 16 times infinity plus 3. Okay, that's... I may only have a bachelor's degree, but that's infinity. 30 times infinity to the fourth power minus 11. Infinity over infinity. My good buddy, L'Hopital to the rescue. So the limit as x approaches infinity. The derivative of the top is going to be 16. The derivative of 16x is 16. The derivative of 3 is 0, so that's my top. The derivative of the bottom, okay, 30x to the fourth, that's going to be 4 times 30. That's 120 x cubed minus 11. The derivative of that is 0. All right, let's have a good laugh. Who do you think is going to win this race? 16 or 120 times infinity to the third power? So if I plug in infinity, 120 times infinity cubed. Oh, man. Well, 16 over 100, 16 over 1,000, 16 over 1,000,000, 16 over 1,000,000,000, 16 over 1,000,000,000,000 is so close to 0, it's practically 0. So the intent for this function is to go flatten out at y equals 0. So without further ado, you might have been bashing your head into your desk or whatever and going, come on, Matt, just use common sense. And the truth is you can. So here are my tips. So if you have the limit as x approaches infinity for a function over a function. In other words, if you have the degree of the numerator over the degree of the denominator. So if I have, for example, x to the fifth over x cubed with the coefficient in front, a over b. So ax to the fifth over bx to the third, and there's just bunch of teammates on the top and teammates on the bottom. Notice that I only care about the degree of the top and the degree of the bottom. So if the degree of the numerator is bigger than the degree of the denominator, then the pursuit towards x equals x going to infinity, the numerator wins. The numerator wins in a landslide. So it's basically going to be, if you apply L'Hopital's rule 3 times, you're going to get infinity over a constant. So that's going to be infinity. Y is going to go to infinity. Now, if the degree of the top is smaller than the degree of the bottom, I just decided to say, you know what? Let's say that the top is ax to the 6th over bx to the 13th. Well, I could apply L'Hopital's rule 6 times, but then I'd rather use my common sense. If the numerator has a smaller degree than the denominator, then that means the denominator is going to win the race towards x approaches infinity. So if the denominator is way, 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 way bigger than the numerator, then it flattens out to y equals 0. And finally, if the degree of the numerator and the degree of the denominator are exactly the same, so it could be x squared on the top, x squared on the bottom, x to the third on the top, x to the third on the bottom, x to the 17th on the top, x to the 17th on the bottom. You and I both know that if we apply L'Hopital's rule 17 gosh darn times, we're just going to keep getting multiples of the exponent to a and the exponent to b, and it's just going to simplify to a over b. So if the degree of the numerator equals the degree of the denominator, then you basically take the coefficients of the leading degree, the leading variable, and you simplify the fraction, or you leave it as it is if it cannot be simplified. And those are the tips that I can give you for the limit as x approaches infinity for a rational function. We're going to have a test after the next video. The next video, I'm going to give you an obstacle course of limits involving infinity, and then I will give you guys a test. It won't be too bad. I just want you guys to get prepared for college. Have a great day, guys.